Now that we've started talking about currents, we have to come up with a way to establish them in a circuit. A battery can certainly do this. We consider the battery to be a source of what's called electromotive force, which is a horrible name and it's confusing because it's not a force, it's a voltage, it's a potential difference. Why would we ever start calling voltage some kind of force? Well, we're going to see there's a reason to move away from the idea of voltage in some cases, and there's at least a not horrible reason for calling this thing a force when it's not a force. We'll see there's at least an analogy to a force. The idea of a battery is it's got chemicals that react in such a way as to give us a potential difference between two terminals. Battery has a variety of important physical properties, but the obvious one is its voltage, or what a voltmeter would read if we connected it across the terminals. You may be surprised to know that a 9-volt battery is really about 10 volts when new, and your car battery is really more like 13.8 volts than 12. If you've ever been stranded by a car that won't start and you needed to get somebody to use their car to jump yours, you might have thought about how nice it would be to have a spare battery. Problem is, car batteries are heavy, bulky, kind of expensive, and you've got to have some way to maintain the charge on them while they're just sitting around, so you won't get one just to keep in the trunk. You might think that if the car battery is about 14 volts, maybe we could take two 9-volt batteries and put them in series, meaning we connect positive terminal of one to the negative of the other, and then the free ends are then at 18 volts apart. This would fit in your glove compartment. They're really cheap. They last a long time. This would be a great way to jump the car. You probably figured out this won't really work. One of the other important properties of a battery is its maximum current, and that's connected to something called its internal resistance. We could take a real battery and model it as this battery that we've been using, the ideal battery, in series with a small resistance. We pretend like this resistor is inside the battery. Of course, that's not what's happening. What's really happening is the chemical reaction in here can only happen so fast, and that means it can only push so many electrons per second out, and that gives us a limit to the current in the same way a resistor limits the current. The reason the car battery is so big and heavy is it's filled with lots and lots of thin lead plates, and that means much larger surface area for the chemical reaction to take place, and that means more current. So it has effectively got a much smaller internal resistor. It still has one, because the car battery, it still can't provide an infinite current, but it can provide a much larger current. The internal resistance of a car battery may be 20 milliohms, something like that. The 9-volt battery is maybe 500 times greater at about 10 ohms, so the most current you'll get out of one of those is about an amp. We can write the voltage that we measure at the terminals as E minus IR, where E is this EMF, the ideal battery, minus the current times the internal resistance. As the battery gets older, we use it, the internal resistance increases. The chemical reaction kind of slows down. This means we can't trust just the voltmeter to check the battery's health. And the reason is the voltmeter, when you complete the circuit by connecting a voltmeter to these ends, the voltmeter has an incredibly high resistance, so virtually no current is going to have to come out of here. You're not asking the battery to do anything that is hard for it to do. So you're probably going to get, even with a dead battery, the voltmeter will tell you, yeah, it's still 9 volts or 12 volts or whatever you're expecting. But then as soon as you try and put it in a device where it's using that battery, where it puts the battery under a load, this drops through the floor and you don't have a battery that will do anything for you. Now, same as with capacitors, resistors are not available in an infinite variety of sizes and tolerances. We have to combine the ones we have to get different values, to get values that we might need. So again, this means connecting them in series or in parallel. We can start by looking at resistors in series. We put these three here in a string with the battery, and we ask what single resistor could take the place of these three and put the same load on the battery. We already found out that the formula for making this cylindrical resistor is R is rho L over A. So what we can imagine is All three of these resistors, they may not have the same value of resistance, but let's say they're made of the same stuff, so rho is the same, and their cross-sectional areas are the same. That means any difference in resistance is just difference in length, but that doesn't show up here anyway. Now, we imagine we bring them closer together until they are ultimately indistinguishable from a single long resistor. The resistance of that single resistor would be rho times the total length divided by the area. So rho L1 over A plus rho L2 over A plus rho L3 over A is R1 plus R2 plus R3. For resistors in series, the equivalent resistance is the sum of the individual resistances. This means the equivalent resistance is always larger than the largest individual resistance. Notice this is what we got for capacitors in parallel, not series. Also, we can see the current through each resistor has to be the same, since whatever charges come through R2 had to come through R1, and they have nowhere to go except R3.